Welcome to the 1959 Nobel Prize in Physics. Give you your quick introduction to this prize. It's actually a pretty simple one, but it's also pretty cool. It has large implications. Went to Emilio Segre and Owen Chamberlain for their discovery of the antiproton. That's right, we're getting into antimatter here. So it's sort of the antimatter version of a proton. And antimatter is basically matter with reverse charge, reverse parity, and ways sort of involving time that are a little bit different. That whole last one where time is different is a complete video all by itself, and that will be someday. But it's not going to be on the Nobel Prize version because that would take me about a half hour to really explain. Now, a proton and antiproton are particles that have exactly the same mass, opposite electric charge, and different quantum numbers. Now, quantum numbers, really easy for me to say, but what the heck is that? Just different quantities that characterize the possible states of a system, or in this case, of a particle. So just little bitty differences in between them. In fact, making protons is actually now a pretty simple thing. Back then, nobody knew how to do it. So how do you make an antiproton? Well, it's pretty easy. You take a proton beam with an accelerator, some kind of way of getting those things to move fast, and smash it into something that has a lot of protons in it. So you take a proton beam, which is hydrogen, where you strip the electron off, shoot it at something that has a whole bunch of protons in it, like iridium, and what you're going to get is some antiprotons are created inside that collision. It does take specific energy levels to get to it, and other things, but like I said, that's going to be its own video because there's a whole discussion about antimatter that really needs to go on. This is just one particle out of it. So what's the difference in between, what's the real difference between a proton and an antiproton? Well, let's take a little bit closer look. So remember, there was a time in the world where we thought the atom was the smallest thing to exist. There was nothing smaller. It was indivisible. We couldn't get smaller than that. And it wasn't that long before this particular discovery where that was true, at least in the history of man. Now, there was Nobel Prizes about that in the earlier part of this video series. Now, the proton actually consists of little other things. So it's made up of stuff. It's not even the smallest. So first we've discovered the atom and said that's the smallest. Then we broke the atom apart and said, holy mother, whatever. There's a bunch of stuff inside here. You've got electrons, you got protons, you get neutrons, you get all these other things. And all those things have been the subject of different Nobel Prizes. So those were only awarded from 1901 through 1959. So the people were still alive within a half a century that made those discoveries of when this Nobel Prize is being awarded for antiprotons. So, this is a whole nuclear and subatomic world we're starting to discover here. Now, protons and antiprotons are a little bit different. The proton is made up of two up quarks and one down quark. The antiproton is made of two up antiquarks and one down antiquark. They're both in the hadron family of particles. They both interact with gravity, both the electromagnetic force, the weak magnetic force, the strong magnetic force. And when they're created, they don't last very long. So you can see in the image here, which was from CERN, where a proton and antiproton meet each other, and then they're both annihilated, and you get other stuff that comes out. And those things don't last very long. So CERN is really good at studying those particles. And those particles are good for things. So what the heck can you use an antiproton for? Because we got protons, these seem stable, but antiprotons really aren't. So is it really like Star Trek? Do they kind of just annihilate and destroy things? Well, kind of. There actually are some applications being examined. So in labs, antiprotons have actually been shown to be potential cancer treatment. So just like a proton beam. So there's all these proton therapies that go on. Well, you can use an antiproton as well, just as well for that, except you get an added bonus. So when you do proton therapy, the proton is not destroyed in the part of you in the process of you doing that therapy, but the antiproton is. So when you bombard the cancer cell with protons and try to destroy the cancerous tissue, the proton imparts a certain amount of energy involved with that collision, along with other stuff. But the antiproton, when it smashes into that cancer cell, you have that smash effect. You also have extra energy in that region that is caused by the annihilation of the antiproton. So it sort of ceases to exist and it takes other stuff with it. So it actually could potentially be a little more effective than just regular proton therapy, but that's still laboratory or level stuff. It's not being used today, at least as far as I'm aware. But it could be something where antimatter actually does see an application inside medical treatment, which could be a lifesaver. I mean, those are things that do truly matter. So I hope you liked this video. Remember, we're about to hit the 1960s, so we're not talking that long ago anymore, historically. Please don't forget to click subscribe and like on the video. It really does help us out with the algorithms, and we will see you on the next one.